But then one of the very large group of compounds really involves the esters. And esters are a lot of natural products are esters. And esters can be formed by treating an acid, a carboxylic acid, with an alcohol. And likewise, it can also be hydrolyzed and back to alcohol and carboxylic acid. So essentially, it is formed by, let's say, COOH. This is the carboxylic acid, and regardless of which group in here, plus another alcohol group. So let's say we call it R prime OH. That gives you the ester where we get R, CO, O, R prime. It's minus H2. So this is the formation of the ester. And ester likewise can be hydrolyzed back to this, and the hydrolysis can be catalyzed either by acid or base, but there is one fundamental difference. Okay, the base catalyzed one is irreversible, whereas the acid catalyzed one are reversible. Okay. So let's see how that really happens. So let's start with any one of the esters. Let's start with something like, simpler to write this, CH3, CO, OCH2, CH3. This is the ester. And the reaction that we expect if we use acid in the presence of water, H2O, then it's going to hydrolyze to the acetic acid, CH3CO, OH, plus ethanol, CH3, CH2, OH. And the process, as we try to understand the mechanism of how this goes, is we can go step by step to see how it really proceeds. So the very first step that you would expect in acid is going to be protonation. So first step is protonation. And in the protonation case, let's say we have the ester and we have hydronium ion in aqueous acid. So that is the proton donor. So the proton donor is the hydronium ion, and the proton would be donated even though you have two different oxygen here. This is the more likely one to take the hydrogen, forming the protonated species now, CH3CO. Now, in the next step, of course, this is partially protonated carbon, and because the oxygen has the positive charge here, what we can see is that this is can be attacked by another nucleophile. In this case, water is going to act as a nucleophile. So you have H2O attacking this, and the positive charge is neutralized. So we end up getting CH3 COH, OCH2 CH3, and OH2 plus. And another molecule of water can remove the extra proton. So you have H2O. The extra proton is removed, forming So now this is a tetrahedral. As we have seen after this step, it gets a tetrahedral structure. And at this point, you can again protonate one of them. Okay. And because you still have acid there, and that protonation can happen in any one of the three oxygen. There is really no particular preference. And it's going to happen to all of them, but the one important is when it gets protonated here on the alkyl oxygen. So positively charged, right? So one of the oxygen from here can now come out and kick out this ethanol molecule. So we get CH3, COH, double bonded OH, plus CH2OH. So we generated ethanol and the positively charged carboxylic acid, and another molecule of water can pick up this proton. So this is kind of the mechanism, and the mechanism has slight variations. You can also write it in a slightly different way, in which rather than protonating these groups, what happens if you protonate one of the hydroxyl group? Okay. And it can actually reverse the reaction as well. And it's not that that's not happening, but that can happening, and then again it starts the process again. So it goes continuously in all kinds of different directions. But the one that is important is when the bond is broken between the ethanol and the carbon, that's when they're separated, and it becomes irreversible after that. And as we have seen before, in this case, water catalyzes many of the steps, and the acid catalyzes the other steps. So if you are to go back, really, what you need to do is to remove water. So if you remove the water, this is going to go back to the previous ester formation. And that's actually the synthesis part really involves that. If you do an acid in the absence of water, the reverse reaction will happen when you make the ester. Now, the reason this is reversible is because of the presence of the water. If you have more water present, this is going to hydrolyze, and if you have less water present, it's going to go back to the ester. So this process is reversible. On the other hand, if we do base catalyzed reaction, which I'll go next, that has a different issue here. So the base catalyzed one is as follows. So the base catalyzed base, you have plenty of OH minus present in there, is going to attack the carbonyl group directly because it's acting as a nucleophile, and the carbon has a slight positive charge, the oxygen has a slight negative charge because of the charge separation. And so this therefore generates the So this is the anion that is being formed by attack of the hydroxyl group. And of course, even though it doesn't have acid, it has water in the system. And water can donate a proton here. Giving you now, again, a protonation step is usually necessary to carry out the subsequent step. Even though it's not acidic per se, it still can protonate with water. And a second water molecule can protonate one of the oxygens. In the subsequent step, one of the oxygen, either one of them, can form the double bond and break this bond. And the carboxylic acid can again lose the proton to generate the carboxylate. But a slight variation of this mechanism, again, is where you can slight variation of the mechanism can be written in which you actually pick out this one as a negative charged species. So if we, rather than drawing this way, so this mechanism has slight variation that you can carry out. Rather than going through this process where the water donates the proton to neutralize the negative charge, the negative charge species can come out here and kick out this one. So that would mean you can generate the acid directly plus an anion, this one. Now this one can pick up this acidic proton, generating a carboxylate. Plus ethanol. And it is believed that this is probably the more possible pathway, because in that case what you generate is an anion, and ultimately, let's say if you use sodium hydroxide, this is the salt that you get, Na plus salt of the acid you will end up getting. So the base catalyzed mechanism, if you need to make the corresponding acid, you have to acidify. A second state is needed. So in the second step then, you just protonate that. You need to acidify to convert the sodium salt to the corresponding carboxylic acid. So that is believed to be the more predominant mechanism, even though no single mechanism actually can be used to describe this. Yes?
What happens to the hydrogen
which hydrogen you're talking about? This hydrogen? This hydrogen is picked up by the anion here, so it becomes the ethanol.
So should it be there next step instead of being anion?
Oh, sorry, I wrote it wrong here. This is no longer is the anion. It becomes the OH, right? Because this is the one which picked up the proton. So it becomes ethanol and a sodium salt of the carboxylic acid.
Where did you get this
That's
sodium?
The second step actually acidifies this one. Any questions? Okay, so the reason the base catalyzed one is irreversible because in the process you are generating a sodium or potassium salt of the carboxylic acid, and therefore that cannot really go back to the ester. And the only way you can get the acid is by acidifying, which involves the second step in the process. So there are therefore two ways of doing this reaction. Let's take any ester for that matter. Let's say
Yeah, he was not having that. okay, so this is really explaining the two methods in which one case you can just use 50% sulfuric acid with 50% water and catalyze the reaction, and you get both products, the carboxylic acid and the alcohol, in this case phenol. And the second case, if you just use the sodium hydroxide or potassium hydroxide, you are going to get the phenol plus the sodium or potassium salt of the carboxylate. And you need a second step in order to generate the carboxylic acid. And that's why this reaction is irreversible, this one is reversible. You just need to remove the water, it is going back in this direction. All right, now the ester hydrolysis also tells us that you can do a lot of different variation of this type of reaction. In other words, if you, rather than using water or base, if you used ammonia, for example, so you can use ammonia in this case, and what you're going to get is the, rather than the carboxylic acid, you are going to get an amide because the ammonia attacks the carbonyl group. So the process is very similar, except that now the attack is taking place by either, rather than OH minus or H2O is by ammonia. And therefore, the final product that you are going to get is an amide. And I'm not writing all the steps here, but you can see how this reaction proceeds. If you use a different amine, for example, then so variation of this reaction is definitely possible to carry out. And there are a bunch of problems in your book that are all related to this type of reaction. Because if you do one, you can figure out the rest of them. And let me just do a couple problems to indicate what they really involve. This is one of the homework problems that I assigned. Okay. What would be this is a 5-member thing, but what would be the resultant compound that would generate by treating this with ammonia? What you expect to see is that the ammonia is going to attack this carbon, right? And form the tetrahedral intermediate, and eventually the bond would be broken here. So what you end up is essentially this. Yeah, and you can rewrite that in a different way. So 1, 2, 3, 3 carbons, 1, 2, 3. And so you have CONH2, and this one is OH. If you are to do the same reaction with sodium hydroxide, NaOH, then that is going to give you, again, this. Right? So these are using the same approach that we have just discussed a little while ago. Now, a little more complicated one is this problem where they're asking, what would you get they are asking what would happen if you treated this with dilute sulfuric acid and heat. And so again, the approach is same, something that we discussed before, where you protonate and protonate the oxygens with the dilute sulfuric acid. And dilute is very important because you have water in there. That's what it implies. And what you are going to get is really carbonic acid, which is the water attacking this carbonate twice. So you end up getting this
plus this alcohol, where you can write just like the way we have the structure. This is what would be the resultant effect, because two water molecules are going to add to this. To join first here, so if you follow the process, the water is attacking the carbonyl, then it opens up the ring, so the bond would be broken between this carbon and the oxygen, and a second reaction will break the second bond between oxygen and the carbon. Okay. So it's going to make two breaks, and two water molecules would be added, giving you this, which is carbonic acid. And you are all familiar with carbonic acid, right? When you drink a soda, that's what you really get. And the reason it forms, it has carbon dioxide dissolved in water, which bubbles. And also this one generates carbon dioxide. So this one breaks down to water and carbon dioxide, CO2 plus H2. Carbonic acid. So this is really a process, again, you are showing an ester hydrolysis using dilute acid. Okay. Any question on this? Any of this problem can show up in the exam.
I have a question. What about when this reacts with a base?
What?
What about when this reacts with a base instead of acid?
This one with
Yeah.
base? Yeah.
Should we know?
If you treat it with base, again, it's going to follow through the same, except that you're going to get a salt. Rather than the carbonic acid, you will get a carbonic acid salt.
Okay.
Whatever sodium or potassium
All right.
hydroxide you use, you'll get the salt. And again, it's not a stable salt. The carbonic acid is unstable, it's breakdown. A different kind of problem is also there. Let's see. Okay, they give you, this is actually problem 19.8.
He does say 4 days.
Okay, so what they're asking is that this compound, it was left for 4 days with water leveled with O18, because the normal oxygen that we have in water is O16, and these are also O16. But if you use O18, this one of the oxygen is going to be exchanged, and they're asking which oxygen, exchanging with O18. And again, you have to kind of follow through the mechanism of how this reaction proceeds. If you follow through that, we'll see that what may happen is that this water can attack the carbonyl carbon, forming O minus and which can then become diol, and then it can go back. Again, the reverse reaction can happen. One of the oxygen can donate the electron pair, forming a double bond, and again kicking out one of the OH group or the water molecule. So the reverse reaction is also possible, and it goes continuously back and forth. So if I now follow this, what's going to happen is that, let's say if I use a marker for the O18,
So this is the O18, and so this is added here, and one of the oxygen is now O18. Now, if this one falls off, then we get back exactly the same thing. But if this one falls off, then we'll get an O18 oxygen there. So eventually what will happen is that they will continue to exchange. If you have a very high quality O18 water in there, eventually all of the oxygen would become O18 here. So that's the one going to be exchanged, not the alcohol hydrogen, alcohol oxygen. Okay. Any questions? All right, I originally thought I would also cover the amides, but they decided against it because there's plenty of stuff in whatever we covered so far. You need to understand the mechanism of the process in most cases. But other than that, I think I'll stop here as far as this goes.
Good job.
We'll stop the, forget about the 19.30 section was in your email, but I'm not going to cover that. Skip that. In chapter 19. So you really need to understand the homework problems that I did, if you can do them comfortably and understand the process. In most cases, it's most convenient to follow the mechanism rather than trying to memorize what type of product is formed. Okay. All right, so in this course, therefore, let me just briefly go over from, I gave you a practice final exam, which you'll go over on Friday. But I would ask you to try that after you have tried the problems from chapter 19. Some of you are still uncomfortable with chapter 17. Do those problems again. And then sit down, try to do the final exam, and then we'll go over that on Friday. Okay. And so what you need to understand, there will be probably a very short question on nomenclature. It's not going to take major part. It's probably going to be like 8 point or something like that. Okay. So mainly you need to focus on acids and bases. You need to understand that very well, which is in chapter 1. So understand all of it, like the conjugate acid, conjugate base, and what their criteria are, how you compare them and figure them out in terms of their strength. Some general rules. Those you need to follow. Okay. The equation, if you can make the acid-base reaction and make the conjugate acid conjugate base, and then figure out from that which one is stronger, weaker, etc. All of these issues are involved. So those are important. In terms of other conceptual things, the stereochemistry is very, very important, which is in chapter 7. The conformations are somewhat important, less important, but you still need to understand some of the processes. So conformations. And by and large, the most important part is learning a series of reactions. We have introduced you to at least probably 20 to 30 reactions. And you need to understand them, which category they fall. There are some characterization as to SN1, SN2, E1, E2, all of these processes are important. So the reactions and their relationship, SN1, SN2, E1, E2, and other types. We completely skip the radical reactions, but there are like hydroboration oxidation, the halogenation,
epoxidation, ozonolysis, and several others. You're familiar with that. So those are the ones that you need to, if you make flashcards or something, make sure that you understand them thoroughly wherever stereochemistry is involved. In some cases they are like the hydroboration oxidation has stereochemistry, halogenation has a stereochemistry specific for that. And so those things are important, and you should make sure that you have a total control of that, right? And the last part that we consider, mainly from parts of chapter 17 and chapter 19, there are a lot of similarities in there, okay, because we looked at the ester formation, hydrolysis, we looked at the reaction with aldehydes and ketones, with amines and other groups, so forth. So the aldehyde ketone acetal formation, acetal and ketal formation, and hydrolysis. And the last part that we talked about, the reaction with amines and water and other reagents, those are all important. So the practice final exam is kind of the preview of the type of question that we will be asked. Many of the questions are repeats from the previous exam, so make sure that you understand them well. Even if you made a mistake last time, don't make the same mistake again. All right, and so I'll see you Friday. We'll go with the exam.